这不也不确定。
这边两门关起来，你就可以认。All right, so good afternoon, ladies and gentlemen. We're going to start the final physics 5 of this tournament. My name is Fang Yulo from National Paranormal University. I'll be the chair for the final 5 of this 5-day. And I think let me first introduce the jurors, and then I will ask all the teams to introduce yourself. So first of all, my name is Fang Yulo from National Paranormal University. I will chair this fight, and then we'll ask the jurors to introduce themselves. Please.
I'm Zhen Yong from Kamkan University.
I'm Dong Yu from Zhongyin University.
I'm Su Wansen from National Taiwan Science Education Center.
The last fight, the topics are pre-selected, and I think that will be one of the best work of all of this tournament. And I hope, but I wish that you will have a very good fight for this round. And now I will ask the teams to introduce themselves. First, start on the reporter team, please.
So we're Team Laplacian, and I'm the captain of the new team. He is Wang Guanyu. He is Huang Yan, Lin Xuanming, and this is Zheng Minhong.
Thank you. And then opponent team, please.
Hello everyone, we're Team Andromeda from National Taiwan Girls Senior High School. I'm the leader of the team. My name is Chen Yuan, and these are my teammates. She is Li Bingxi, she is Chen Liqing, and she is Cai Man, and she is Dai Zhenxi. Thank you.
Thank you. And then the reviewer team.
This team Do from Taipei High School. I'm Captain Leader, and we have Zhang Wuxian, Xu Minghe.
Okay. So all the teams have introduced themselves. And any other announcement that I should make?
No.
Okay.
I just take it.
So, and then for the first stage, we will have, we're going to, okay, then the topic is number 4, diamond magnet. So we'll start from the preparation of the reporter. So, please start the clock.
Me.
Okay. And also, during the preparation time, I will ask all the teams to write the presenter's name on the blackboard, please.
my
So you're going to start?
yeah, I'm going
Okay,
to start.
please start the report.
Okay. Hello everyone. I'm the reporter of the timing magnets, and I'm from La Paz. Okay, so this is the problem statement. Attach a rod assembled from cylindrical neodymium magnets horizontally to a vertical ferromagnetic rod. Limit the motion of the magnets to the vertical direction. When a ferromagnetic rod is spun around this axis of symmetry, the magnetic rod begins to climb up. Explain this phenomenon and investigate how the rate of climbing depends on relevant parameters. So our key questions of this problem is, when does the magnet climb and what affects the rate of climbing? So this is our outline. And first is the phenomenon and setup. So the motion of the magnet, there's a climbing motion and a descending motion. And the climbing motion has a x direction angular velocity and a z direction velocity, like the axis coordinate definition is like this. So I place the VB here. So it climbs. And another one is descending phenomenon. So it is unstable phenomenon and it just descending. So, but in some case the magnets can climb stably, but some case the magnets become shorter. Climbing behavior will not be stable and sometimes fall down and sometimes just stuck on the rod. So, but we only care about when does it climb and its rate. So we only focus on the climbing part of the motion, and climbing rate means that the speed of climbing part denoted by Vm. So this is the graph. This is the height of the magnet, and this is the time. And there's some motion that climbs and stops. So we only want to analyze this velocity, and there's climb and descending, but we only care about this climb. So this is the climbing stably situation. So it just climbs stably, and it is a constant velocity. So external setup. There's a spinning iron rod, a wood for constraint, for limit the magnets to the z direction motion, and a magnet. And there's some motor to spin the iron rod. There's a up motor and a down motor, and the middle of this is an iron rod, and they are spinning. So the magnet setup, the magnet configuration, it consists of three parts. The first part is the weak magnets like this, and the strong magnets like this, and the n weak magnets. So why did we do this? Because we want to control the L, the length of the magnet, and it worked. The weak magnet is the force supplied by the weak magnet is negligible. So because the force supplied by the neodymium magnet is too strong, so we can neglect the magnetic effect by this weak magnet, and we measure the total mass by this. And we want to prove that the magnetic force is not related to the n. So this is the graph. So there's magnetic force by this, and this is not important. So when n goes up, the Fb, the magnetic force is likely to be a constant. So this is our theory model. We first investigate the geometry. So we define the h by the constraint distance, and r by the radius of rod, l by the length of the magnet, dm by the diameter of the magnet, and n by the number of the magnet. So we have found the relation between L and N. So it's like this. We just measure the length of this magnet and this magnet. So and another one is the phi and S. So S is defined by the midpoint and the contact point, this offset distance. And the phi is defined by the contact point angle. So we can solve the geometry, like we can find H equals to this equation, and we can solve the phi by solve this equation. So phi is like this. And I want to mention that this diagram is we looking from top view. So if you look like this is the top view. So another one is the free body diagram. So we knew that the constant V and omega is the magnetic motion. So we can find that the total force and torque is 0. So this force exerted on the magnet might obey this equation. So we calculate this. So we by this sigma f and sigma tau equals to 0, and we can solve the S, the offset distance, by this equation, complicated equation. So it is related to H, dm, R, and L, and UK. So why we investigate S? Why we calculate S? Because we want to assume some thing. It's just the magnet is purely on the iron rod, but the contact point is not the midpoint, but the bottom point, because the magnets will slightly inclining by the gravitational force, so it inclining sometimes, but the contact point is the bottom point. So we just we know that the pure rolling must obey the contact point velocity is same as the rod, so we can calculate this equation. So for the O, we can calculate the timing rate Vm. Timing rate is proportional to the omega r, and the K is the efficiency that omega r transmit to the Vm. So it's a proportional coefficient. And the K, we can obtain it by calculate S. So S is related to these 5 variables. So this is the plus of the K and R and L. So in our experiment, H, dm, and mu K is not varied, it's controlled variable, and we only vary these variables by this R is region, L is region, and N is the measure. Yeah. So this is the plot. So when greater L is, the greater K is, the greater R is, the greater K is. So these are theory outline. And the condition of climbing is also a theory. So when the weight is small enough, the mg, the gravitational force, is small enough, so the contact point will not be the bottom point. So it won't climb. But the weight is too heavy, the magnetic force cannot support it, so it just falls down. So N had the upper bound and lower bound. And experiment, the first experiment we investigate how Vm changes with respect to omega r, and in theory it is proportional. So in our experiment, we do observe the proportional behavior, because the blue point is our experiment and the red point is the theory. So we can say that the linear regression is just linear, and the K is the omega r trans the conversion efficiency from the omega r to the Vm. So the K is this, and we can also calculate the K. And in theory, we can show that the K is related to the S, R, Vm, and S is also related to these five variables, and we vary the N, which is vary the L. So we fix the R by this number, and and vary L. So we can also find this experiment and the theoretical curve, and we found that it also very match. So the last one is how this K change with respect to R. So we fix the L by this number, and we vary R. So the x-axis is R, and the y-axis is the K. So K is the Vm divided by omega R. So the blue line is theoretical, red point is experimental data, and it also matches. So we completed find the Vm, how Vm varies, the variables that change Vm, and the relationship that Vm change, and Vm stands for the timing rate, which is the problem statement want me to investigate. So this is the condition of magnets timing stably when n is between these two numbers. The magnets can time stably, and these two numbers is related to r, so the radius of the rod, and n is like the length. So so two lengths, the gravitational cannot, the contact point is not the marker point, and too much it will fall. And our conclusion is we obtain the relationship between time velocity and the related parameter quantitatively. And we did the experiment relation of Vm and omega r, RL. So we do these three variables, and the experiment data and the model matches. So this is the most important. So where theoretical is success. Okay, thank you.
Time is up. It's time for opponent to ask short questions.
I'm the opponent from T Andromeda, and I'm going to answer your question. And so, for the reporter, my first question is do you think there is when you zoom in the time that you observe, like if the time interval is really small, do you think it will still do you think the rates will still increase like smoothly?
Yeah, because.
You think yes, it will still move smoothly.
Because we only talk about the smooth part.
Okay, but actually in the real world they will be not smooth, right? But you only choose the smooth part, but there's a part that is not smooth.
Yeah,
right?
but it is under some condition.
Okay.
Under some condition. Under some condition.
Okay, it's okay. I understand you. Okay.
Okay.
Okay. So.
It will be smooth. Yeah.
Okay. So what is the role of the blocker?
Blocker.
Yeah, you use a thing to block the magnet. What is the role of that?
Roll. Do you mean
the wood? The wood. What is the role of the wood? What can the
roll is the density?
No. What can the wood do in your experiment?
Just for the constraint, limit it into the z direction, like the problem statement say.
Okay, so you think it's just putting in a vertical direction and
Yeah.
no other use?
There's some friction. There's some friction.
Okay, and during the timing process, have you observed any vibration or instability?
Okay, not, but in descending.
Okay, it's okay.
Yeah.
No, okay. And my next question is, so have you observed any stick-slip phenomena?
Okay, so actually yes, because there's stick and slip, stick and slip.
And do you think it's still smooth with the stick-slip phenomena, or it's not smooth, but you just choose a smooth part?
Yeah, I just choose a smooth part.
Okay,
It's the
thank you.
timing rate.
The opponent has 2 minutes to prepare.
没有啊。
Okay, now it's time for the opponent to give 4 minutes speech and later discussion with the voters. Please go ahead.
Hello everyone, I'm the opponent from Team Andromeda, and now I'm going to oppose problem number 4, coming magnet. So here's the problem statement. Attach a rod assembled from a cylindrical neodymium magnet horizontally to a vertical magnet rod. Limit the motion of the magnet to a vertical direction. When the ferromagnetic rod is spun around its axis of symmetry, the magnet rod begins to climb up. So we are going to explain this phenomenon and investigate how the rate of climbing depends on relevant parameters. So in my further discussion, I'll be mainly focused on number 1, the explanation of this phenomenon, and the second one is how the relevant parameters affect the result. And next is a review of the report. In the theoretical model part, he talked about force analysis and free body diagram. His pros is he has explained in what condition can the magnet climb up or it will fall down. But his cons is he didn't explain the phenomenon clearly. He also didn't have the force analyzed between the rod and the magnet and the blocker. He didn't really use his theory to prove that why will it climb up. He just used the force analysis to get the formula of his velocity. And for experimental setup, he put a rotating speed of the rod and the magnetic force. His pros is that he has clear demonstration video of the phenomenon. However, he didn't explain what the blocker is for and only consider the motion of the smooth part. And I think this is really wrong because as you do an experiment, you should observe every part of it. You cannot just look at the part that you like and you think it's okay to analyze and choose the smooth part. And for data analysis, he talked about climbing rate of the magnet and the rotational direction of the magnet and the condition of climbing. And his process, he has sufficient data points to investigate the phenomenon. However, he lack of error analysis and didn't explain why the magnet can climb up. And his error bar is really big that it can basically cover each error bar together. And the next is the discussing point. And in my third discussing time, I will be talking about first the force analyzed between the rod, the magnet, and the blocker. And also the reason why the magnet will climb up. I think this is really the important part of this question. And also, why will the magnet climb down? It will also climb up, or it just have two conditions, climb up or falling. And the fourth one is, what can prove the stick-slip phenomenon besides the motion of the magnet? And he also said that there's stick-slip phenomenon, but his VT graph looks really smoothly, so I'm going to discuss this deeply with him. And the next part is for experiment setup. I'm going to talk about is the magnet vertical to the rod and the role of the blocker, because I think the role of the blocker is more than what he just said. And also it's the magnet rubbing during the experiment. And for data analysis, I'm going to talk about how relevant parameters affect the force exerted on the magnet. And the reason of the error in the data graph, because the error is really huge. And the error analysis of the climbing rate. So now I would like to invite the reporters.
So please go ahead with the discussion.
Okay. So my first question is that you say you have observed a stick-shift phenomenon.
Yes.
Correct? And do you think that velocity will still be smooth with the stick-shift phenomenon?
Not.
And then what makes you think that you can just choose the smooth part and observe it instead of, because I think the stick-shift phenomenon is the main reason of why the magnet will climb up, but you kind of just ignore the fact that there's the phenomenon happening and choose the smooth part.
Okay, when we observe that when it sleep, the magnet doesn't climb. It just stick on the rod or descending. But when it stick on the rod, it's just a bottom point stick on the rod, so it is a pure rolling. So it will climb. So the stick part, stick slip motion, the stick part will cause the climb. So sometimes there's only stick part. So
If there's no slip part, why is there a stick part?
okay. So stick part is related to the I want to say that the slip part also only important in the descending. So we can see that this part is only climbing. So we only want to investigate the rate of climbing. So the rate of climbing is just this part. So you said that I only focus on the smooth part, but smooth part just stands for the climb part.
So
So
it didn't say climb up or climb down. Maybe it will climb down. It just say climbing.
what is climb down?
No, but like even I know, but like even though the reason why it will happen, it will climb up is because of the whole phenomenon. You cannot just ignore the part that is the relevant part that will make it climb up.
Okay, so in our theory, why does it climb up? It's because this point is pure rolling to the rod. So in the stick slip phenomenon, the stick part is this point is pure rolling. So it will because this is rolling. So I think that it is rolling, and the rolling velocity is from this direction, and the rod point velocity is from this x direction, you know. So it must be a vm up velocity to.
Okay, so let me clarify. You say that there is only a contact point between the magnet and the rod. It's not a line, it's a point. Is that what you're saying? Okay. Then why will it be a point?
Because the gravitational force incline it.
Yeah, but you put your magnet here, and then when it stays here, there will be a contact like here. And even though there is static phenomenon happening, it will not make it tilt this way. Because because
not this way.
Yeah,
So I
because blocker is
said
here.
that. So I said that it climbed slightly. Yeah. So when it inclines slightly, no matter how small, it might be this degree, 0.1 degree. I don't measure it, but it is enough to say that the contact point only have one.
Okay, so if you think the contact point only have one, can you draw the force diagram to prove that there's only one contact point?
Okay, so it is like this, and the rod is like this, and is a magnet. So it will be a gravitational force like magnetic force, and like my equation is Q, denoted by Q, because there's a like this way provided by the contract, and there might be some friction. So friction is like when we from top view, my slides has it. So it's like this.
Yeah, but okay, this is the magnet and this is a rod.
Yeah.
Or this is a magnet.
Yeah.
This is a rod.
Yeah.
Which one?
This is rod from the top view. From the top view. So this rod is magnet. Yeah. Sorry.
Yeah, but there should be a line instead of a point.
Because it is from the top view. So for this it is from this view. So it is 3D. So so from this view you can observe.
Okay,
It.
so do
But
you
only
think that-
we assume it, but we didn't observe in.
So
the
you
experiment.
just assume that it is a point, and you didn't see a point in your phenomenon. You see a line.
Yeah.
Yeah. Okay. So
But
do you think that is?
in some case, I mentioned that it will fall, right?
Yeah.
When the length is too big, the torque provided by this is too big, so it will fall. It will fall. So it will climb also. So the incline angle is very big. I observed it.
Okay. You.
Okay,
I know.
so I
Okay. You
can-
observe it, but still, like it's really big. But you say you didn't see the phenomenon. Like you just assume that it will look like this. But what you see is actually a line. You just say that it's just a line. So
But
if
you-
it's just a line, then the theory you use is maybe it's not correct because the theory you use is a point. And also the part that you just choose the smooth part of the velocity. Well, why can you do that? Like this, the phenomenon contains the whole thing. You also have to think about the velocity when there's six slipping. Do you
Okay,
agree?
so it is like, okay, I can agree with you like the stick, but only the stick part caused the climb part, and the slip part is just an unstable part. So we only want to know is the like the climbing rate, you know. So we only want to know the climbing rate. So the climbing rate is provided by stick. So stick is the contact point doesn't move.
But why won't the timing rate affected by the part that is dropping? It is still a rate.
Drop.
But you say the velocity will
But
go up
it's
and
not
down, up and down.
climbing. It's not climbing. We only focus on the climbing rate, but not the standing rate.
Okay, it's okay. And can we look at your data?
Data. Which page?
Page 25.
This one.
Yeah. Can you explain why the theoretical curve will be here and then go up?
Okay, so this part is not real because in this part,
Okay, let's continue.
in this part, it won't behave like a climbing phenomenon because when it's too short, it won't climb. When it is short,
Your
too short,
your
n
x-axis is
is the n, so it's the number of the
the magnet and the y-axis. What is the y? What is the y?
y-axis is the Vm divided by omega r. It is represent how omega r like converts to the Vm, the divisions. Yes.
Okay, so you say that this part is not correct.
Yeah, because this the boundary condition is between 5 and
Okay.
yeah.
then-
So it is like in this case the 5 and this 15 is the boundary condition. When it is too small or too large, it won't be correct.
Okay, so then my next question is, you are saying that your data point it kind of fit the curve of the theoretical line, so you think it's accurate. But you have a gigantic error bar.
Gigantic error bar. Okay.
Like maybe your error bar have been here and here and here and here. And how can you say that it will fit the theoretical curve?
Okay, so I might be the graph might be, I don't know why this.
You cannot explain why
Yeah,
there's.
it's maybe the unit is wrong and my code is wrong. So
Or
sorry
there is a possibility that your theory is wrong or your experiment is wrong. So that's why you have a gigantic error bar.
gigantic error bar. The error bar is not produced by the theory. It is
I
produced.
know it's produced by your experiment. That's why it's called error bar. But still, you cannot explain why do you have such a big error bar. Can you explain why?
The error bar is produced by like each point I do the linear regression because it is k. It is a proportional coefficient. So each part I do this graph and find this slope and I can give this point. This error bar. So error bar is
maybe the theory is kind of wrong or your experiment is wrong. So okay, then my next question is, what do you think is the main reason that will affect the climate rate?
okay. The main reason is omega r is the angular velocity by the r and the radius of the rod and the diameter of the diameter of the magnet.
So you think it's the
And there's also another factor I didn't change is the mu k. Yeah, the coefficient, the friction coefficient.
The time is up. So,
Thank you.
please make a 1 minute summary.
Okay, and I'm the opponent from Andromeda, and it is my summary. And in the discussion time, we talk about whether he can just choose the smooth part of the velocity. And after the 12-minute discussion, I still don't think it's okay because he should investigate the whole phenomenon. And also, he keeps saying that the magnet only has one contact point to the rock, but he said that. He assumed that it will happen, but I can observe the phenomenon that it will be a point. So I still think that it should be a contact line instead of a contact point. Therefore, maybe his theory has something wrong because first he chose a point instead of a line, and second, he didn't really consider the stick-stick phenomenon part. He just chose the smooth part. And then for data, he has a spherical curve, but he said one part is not correct. But if we ignore that part, there is still a really big error bar in his experimental data, and he cannot explain it. He said it's kind of like he said that it's maybe something mistake. But I think it's really important because if error bar is so big, then you cannot prove that your theory is correct. That's all from my theory. Thank you.
So now it's time for the reviewer to ask both teams questions.
So now I have several questions to ask both of you guys. So first one is, what is the influence of mass in this experiment?
Okay, the timing condition. When the mass is too strong, it won't climb. When the mass is too slow.
Okay, thank you. How
Yeah, I
about
think that if the mass is too high, it will drop, and if the mass is too slow, it will come.
okay, and this one is for opponent. So you mentioned about the stick phenomenon. So could you explain like how this happened in this experiment?
Yeah, because the rod will rotate like this, and so the magnet will go this way. However, there is a blocker here that's blocking the magnet to go that way. So it's blocking here. So the contact point on the rod will still moving,
Okay.
and so push it back.
Okay,
so
thank you.
happen.
And this one is for reporter. So you mentioned the magnets will roll, but what causes the magnet to roll up but not roll down?
Roll only has like the angular velocity. So what caused is because the contact point of the magnet and the rod is the velocity is the same.
It's the same. Okay. And next one is also for opponent. So you mentioned in some condition sorry, for reporter. So you mentioned about in some condition the magnet will flow. So can you explain further on that?
Okay. So if like this page, when the weight is small enough, the contact point will not be the bottom of the magnet, so it won't rolling and coming back. And when the weight is too heavy, the magnetic force cannot support it, so it will fall down.
Okay, so this one is for reporter as well. So what's the boundary condition for the minimum angular velocity for the magnet to move up?
Maximum angular velocity.
Yeah, like minimum or either maximum.
Okay, minimum. I didn't observe there's a minimum boundary condition, but for the maximum condition, because in the maximum condition case, my experiment cannot supply such a big angular velocity. so I don't observe.
So this one is for opponent. So you mentioned a lot like how blocker will influence the experiment due to the friction, right? So can you like explain more on like the influence about the blocker?
The influence of the blocker is that it will cause the phenomenon to happen, and I think it's giving a normal force instead of a friction.
Okay. So next one is for the reporter, and so so there's a huge there's on page 7 there's so can you explain on what causes the difference between those two graphs on page 7?
This
7 page 7. Yeah. Yeah.
Oh.
This one.
Okay, this one is the climbing part, and this one is the climbing part, and this one is the descending part. We don't care, and this the.
Sorry, the time is.
Okay.
So we only have 2 minutes to prepare.
需要切换吗？还是会自己切？
他们是这种。
那你从2个地方看到自己先进化，从上面有一进阶，你就
Please go ahead.
So good afternoon, honorable judges, fellow contestants, and guests. I'm the reviewer from Team Wei Go Go Go, and right now I'm going to review problem number 4, climbing magnets. So here's the problem statement. Next. And here's the theory and experiment that the reporter used. Next. So here's some pros and cons for a reporter. So I think he has a clear explanation of the experiment setup and also a clear demonstration of the phenomenon. And there's some cons such as I think the assumption is not provided, and they fail to explain the most important question: why does the magnet collapse off? And also the experiment seems to focus about the friction and magnetic force, and they didn't consider about that. And they fail to compare the theoretical model and the experimental model, while not providing any error rate. And error bar is very big. And they also fail to discuss the influence of the blocker. And here's pros and cons for the opponent. So they ask multiple key questions, and they point out the slipstick phenomenon, which is one of the most important factors in climbing. And for cons, they have some wrong attacking points, such as the contacting point or it's a line or a point. And they also they did not give any like contributing suggestion for the solution. So here's a discussion. So the opponent says they mentioned the slipstick phenomenon, and they only talks about the smooth part. The reporter responds with when slip is not climbing, so the stick part is the cause of the climb. Slip part is only a cause of the climb. However, our opinion is that the reporter might have misunderstood about the slipstick phenomenon. So both slip and stick is important to this climbing phenomenon. And next one, opponent says, is there any one contact point or there should be the line? And reporters say they assume it to be a point. In our opinion, we agree to the reporter, so we believe that the torque caused by the gravity and the friction will cause a slope distribution of the normal force, where the bottom part is bigger. Next, the opponent says, why is there like such a big error bar. The reporter say they have an unclear answer about it, and we agree with the opponent. The error bar shows there are some flaws in the theory. And here's some questions that we asked some of them. So first, I asked the reporter, like, is the contact velocity the same? And our opinion is that the magnetic force causing the torque way larger than the gravity force. Next one is, what is the influence of a blocker and the slip phenomenon? So the opponent says it will slip and the blocker will make it to stick back to remain its position, and the block will give normal force and friction to the magnet. And our opinion is that we agree with the opponent. Next, here are some missing points. So first, I think they need to do some research about the magnetic force analysis. I didn't see any of magnetic force analysis in their experiment and in their theory as well. And the magnetic field distribution of the magnet is also not shown in their experiment. And I think they also should have like quantitative results since it's asking the problem statement. And they also should test the magnetic force and friction coefficient, which is the μk, like we mentioned a lot in their both experiment and theory. However, in their theory, the μk doesn't match with their experimental data of the μk. So I think that's one of the major flaw. Yeah, that's all. Thank you.
Thank you. So the reporter, you have 2 minutes to make your concluding remark.
Okay. So the concluding part. My own contribution is I write the relation of the climbing rate and the relevant parameter quantitatively. And I did the relation experiment, the experiment of the relation of Vm, which is climbing velocity, and omega RL. So the experiment data is, and the model is matches. And why is the error bar is huge? Is because the error, the other experiment, and there's there's only other point is the error bar of the other point is small. So the control the parameters while keeping others constant. Yeah. So in short question, we think that the rolling smoothly and small interval, and we only consider the smoothly because it's under some condition. Under some condition, there's not small, but we only focus on the smooth, which is climb. Other is descending. So what is the use of the wood? And so we think that it's a constraint and a fiction. Also the normal force, and I showed in the free body diagram. And the vibration at ascending stage and stick and slip phenomenon. So I have observed it. But the main focus of our experiment, the climbing rate is about the stick, and slip only contribute to the descending. So the slip phenomenon, opponents in the velocity is not smooth, but in the problem statement, they let me investigate the climbing rate, which is the climb, the velocity of climbing. So this is my response. And the contact point is reasonable hypothesis due to the result.
Thank you. So it's time for jurors to ask questions. Any questions from the jurors? Yeah, please.
Maybe start from the reviewer because you mentioned about this new K. So I just want to ask you about, do you think it's important in this case is new K or new S, new S? Okay. And maybe same question with the reporter and the opponent. You can mention your opponent.
Yeah, I think it's really important. Yeah? It's really important.
When is this important? Do they both play important role or one of them?
So the mu k, like the mu k or the mu s will be the main reason I call it stick or stick, you know.
I think both is important, but I think both is important because both of the mu level cause the stick phenomenon to happen, but because still like the rod is still rotating, so maybe mu k will act more on this phenomenon.
So I think mu k and mu s is both important, and mu k is I measure the mu k in our experiment. So like this. So mu k causes the friction, kinetic friction to this point, and the mu s is the contact point. So the contact point will apply a mu s. So that is both is important.
Can I add something to the previous answer? So I think when the mu k happens, mu s happen, it actually will cause a magnetic slip, and when the mu s happen, it will make the magnet roll.
And the question is from jury members. Yes, please.
Do you think stick and slip is essential to the?
Yeah. So it is the condition of climbing.
So if there is no stick and slip,
Also, when it descend, it stick. When it descend, it slip, and when it climb, it sticks. Yeah.
do you have the same?
I think that if there's no stick-slip phenomenon, then I don't think the magnet will still climb up.
Yeah, I also agree with the opponent, and I want to add something to that. So when the magnet slip, so actually shift to like a little bit to the other side of the rod. And the rod, it will cause like space for the magnet to stick on the object like that. Yeah.
Other questions? So then I have one question for all three teams. So concern for this motion. So what is the function or what does of the friction? So it offers force to climb, or it offers the force to stop the climbing. So which function does the friction offer? Okay. Maybe start from the opponent, please. So I would like to start with the opponent for the transmission.
So the friction will let the magnet rotate, and because it will because when it will rotate in a point, and it will rotate up. So I think the friction makes the magnet rotate, and then it will rotate up, so it will further cause the climbing.
Okay, review.
Yeah, I also agree with their statement. So, like I just showed before, maybe there's like some clarification about that. So when I mean like slip, you will like roll on this way and like make a magnetic climb.
So if the friction, kinetic friction exists, there's might be a offset distance from the midpoint to the to this point, the contact point. So there's a S denoted by the offset variable. So if this exists, this contact point velocity is to this direction. So to this direction, we can observe that there's a vertical velocity to this and a horizontal velocity to this. So the horizontal velocity to this, it can provided by the friction. So the rod is like to this direction, to rod to spin, and so its velocity is to this direction. And another.
Please be short. So it is helping for the climbing or not helping for the
helping for the climbing.
Okay. So I think the time is up. So let's give the jurors some time to make the scores. So thank you. Please sit down. Please, keep your manner.
Sorry.
Okay, I think the jurors are ready. So let's show the scores for the recording. Let me read from my side. 4, 5, 5, 6, and 8. Okay, then it's for the opponent. 5, 6, 7, 6, and 7. Then the scores for the reviewer. 5, 7, 7, 7, and 7. So, alright. It's time for the jurors to give some brief comments. I will start on me because I have always the lowest scores for all the teams. First of all, for the reporter, so I don't think for me first of all, as opponent mentioned, for the phenomena explanation that is not so clear. Secondly, for all your data, actually we don't understand even from the diagram and also from your report. We don't understand under what condition that you are working on, and also so that we cannot have a good interpretation of the data from our side. And also, I think for your model, because the whole motion is consisting of, for example, at the present, all the people think that it's based on a stick and stick. So, in principle, your model should describe all these parts. So you only select the climbing part that is not complete. So and also the most important thing is that for your model, you're using periodic. Basically, you should later discuss the deep deviation. So from your measurement data and also your model, and so that you can have some better understanding of the parts. Okay. Second is for the opponent. Basically, for your part, that you during the question and the short question part and the speech part, that is okay. But actually during the discussion, I don't see much. I don't hear much from you because you raise some questions and point out some drawbacks. But what's your own opinion about that? Or what is your contribution to the solutions? I don't get it. Okay. So that is the pity. And for the review, so you have 4 minutes, but in the end you speak only for about a bit more than 3 minutes. And in your speech, I don't see you make a summary of the report. You just say the pros and cons. And also for the opponents of about 3 minutes of presentation, I don't see your summary about their opinion. So that is the main drawback from your review. That is my why. So all of you get quite low grade for me. So for the higher grades, any of the jury member would like to give some comments or give some praise for that. Okay. If not, let's thank all the teams for this stage of fight, and hope you will enjoy the next 2 stages. So we have a 10 minutes break, right? And please remember to change.